Okay, so I'm going to start share screen. All right, so we are now sharing. I did check the fine-tune, the Scholar GPU. So I just wanted to show you guys it. So you can see it did finish. The job did finish the training. It gave us some metrics. So this is basically the whole example that I was running, okay, from Hugging Face. Basically, I was just trying one example that I grabbed. And so I was, it's basic. This is the model is trained, and then at this point, what they had is you have a metric basically to calculate how good it is, right? So you start to use it to do some inference, and that's basically it. So we were able to start with some data, right? We downloaded the GPT-2 and its tokenizer, and then created the data set in just the way that it needs it. And then basically the steps are that you create the training arguments, you have the trainer, you run the trainer basically, and that's it. Okay, so that's the way that Hugging Face has implemented these models. All right, so that finished. Just gonna check my quota here. Right, so it ended at 19. And if I go back to the dashboard, I want to see. Not sure if it's been 37 minutes left on the GPU, so it's still there, basically. All right, I'm done with these, so I'm just gonna the job ended, so I'm just gonna close these out. And hopefully that made sense. That one. So that's GPU Scholar basically. And you know, we saw that it did a job. All right, so the next thing, so we finished GPTs basically, okay? So I would consider hopefully that you got some of the main ideas of it. We got through the code. This is the output. Now we're gonna move on to encoder-only models, okay? So just to finish this up, so once again, we want to go back into the original transformers diagram. Okay, so this is the original Vaswani paper, right? There was an encoder and a decoder. So again, the inputs come through here, go through the encoder, come out here. Then those inputs plus the input to the decoder are all combined to produce a final output, right? That's the original Vaswani paper. They split this into encoder and decoder. So GPTs were this half and encoders were this half, okay? So that's what we're going to talk about now. So what did they do with these encoders here, basically? But if you look, they're very similar. They got inputs n by 40 becomes n by 40 by 512. That's the same. Then these go through all the encoder layers. These go through all the encoder layers, and then you get n by 40 by 512. Effectively, what happens? The only difference is that there is no final layer. Do you guys see that? So in the decoder, about here, you get n by 40 by 512. So out of this last decoder layer, and then that n by 40 by 512 becomes n by 40 by, let's say your vocabulary size is 85,000. So it's n by 40 by 85,000 in the decoder. But here, it's only n by 40 by 512. So then the question is, what is that for? Because what is n by 40 by 512? Let's say that I run a sentence through this, right? when you look at n by 40 by 512, what is that? It's an embedding. It has no meaning, right? It's just, I mean, it has meaning to the transformer maybe, but we can't really know what it is because it's just weights, just a whole bunch of weights. All right, so that's kind of what it, what the idea is here. So let's go then to the description. So I provided the description, read through it. Hopefully it makes sense. Okay, so encoder only, they're very similar. I provided here the code for it, and if you know, it's exactly the same, except that the architecture is missing that last part. If you notice here, it's blocks, then L and F, right? And in the other one should be this one. Blocks L and F, and there is this thing called the head. You see that? So basically it has no last layer called the head. Usually these head layers, you'll see them a lot, even in Hugging Face classes. They'll say something head. They're the last thing that you add to it. Okay? Now keep in mind, so you would have an input, it would go through all the layers, and the purpose was to take that encoded, remember that the original transformer was for language translation. So it would take an, it would take an English sentence here, encode it into something, and that over here, you'd have like the Portuguese sentence, it would go in plus the encoded English sentence. It would use all that information to produce the translation, to learn to translate, basically, okay? So that was the original, but now they had this idea, okay, I can give it a sentence in English, and what do I do with the embedding, right? And that's what created the BERT models. So they're just missing that head, so obviously then you add a new type of a head. Okay, so we're gonna go now, so hopefully so basically it's just missing that last part. You saw it's missing in the code. So encoder only models, right? You can see it's missing that last head. All right, so now that brings us to the BERT model. So BERT model stands for bidirectional encoder representations from transformers. Okay, so the idea here is basically here is a BERT model. Okay, so the BERT models were trained originally in the paper based on two approaches. Okay, so they were trying to once again create a transformer that did something. Okay, so all they did, if you notice, is the sentence goes in English. This is a transformer, but we're ignoring now all the layers because you guys know that all that matters is n by 40 by 512 goes in, n by 40 by 512 comes out. Do you see that? And then the only trick is, once again, you add a head. And notice this head is very similar to the GPT head. In fact, it's the GPT head. You have an FFN neural network layer that maps into vocab size, once again. The trick is, though, that you are going to use this idea of masking. So whereas before you were predicting shifted sentences with GPTs, right? With BERTs, you're not predicting shifted sentences. Instead, what you're predicting with BERTs is these are called masked models. Okay, so the idea is, you train based on the masked language task, or you train, there's a second one called a two-sentence task, but let's look at the first one. So the point here is you're going to mask. So for instance, we have the Princess Mary entered the dark woods of Engar, right? And so it's got these other tags that are used for various things, right? So it's got like padding tags. It always has a starting CLS tag, and it's got this masking tag. So randomly, when they were training BERT models, which are encoder-only models, they would mask one of the words, right? Woods, for instance. And so the model then has to predict that word. So basically, it's got all the embeddings, and it's going to take that embedding and map it to vocab size. So then once it predicts the word, maybe sometimes it says the Princess Mary entered the dark trees of Angar, right? And it's going to compare it to woods, and basically the losses, the weights are going to be updated accordingly. Okay? So that's it. That's the mask language model. Eventually, it should learn to predict the right word. We saw this when we were doing Hugging Face transformers. I would mask some word, and then, you know, the sheep went on the mountain, and then it would tell us something. That's how it was trained, basically. Do you guys see that? If you notice, you have tons of sentences, right? All you have to do is take all the books in the world, you take the sentence, that's your same input and output, and the key thing is to randomly mask it. I think they mask like 20% or something of the words, and that's it. And then you give it tons of these examples, and eventually the BERT model is a very good language model, right? Is this a pre-trained model? Got it? All right, the next approach that so this is one approach to train a BERT. The next approach that they took to train a BERT is this one. This is called the two-sentence task training. So what you have to think about historically, how everything was done in machine learning, you either had unsupervised learning or you had supervised learning. And in supervised learning, you always had labels, like you had a sentence and it was happy, sad, whatever it is, right? They were thinking, how do we train these models without labeling, right? And so they invented these ideas of, okay, well, let's just start with something simple, because we have a sentence. If we give it the sentence over here and just mask it, we have the information. That's the label itself, right? The next problem they thought about is something called next sentence prediction. So that is, you have a book, so you have a sentence, the car is going really fast, and then it crashed. Those two sentences would be taken out of a text, and you know, because you took them out of the text, that one sentence follows the other one. You see what I'm saying? And then, so that's what they did. They would take one sentence and then put this symbol needs to be there, it's the separator, and then the next sentence. Okay? So the owl flew here, then it flew away, right? So it's two sentences. But what do you do here? You have notice this is a nice trick. You have n by 40 by 512, right? Goes in. N by 40 by 512 comes out. However, there is this. There is this symbol called CLS that goes from the beginning, and it slides through to the end. And that is just, neural network multiplications that are happening. At the end, you add a feed-forward layer, and then that just predicts a vector of size 2. That's a classification effectively. So when you basically disregard all this information, but because it's all connected, right? All the information that feeds in through here eventually needs to tie to this output over here. Do you guys see that? So the transformer basically takes in the input. It's got this symbol separator always. It's got this symbol CLS always. It's got all the layers, all the encoding layers. And then somehow it needs to learn to ignore all these outputs and just basically this is the only thing that matters. This output here, because remember, this output is not just based on this, but it depends on everything. And this is just a neural network layer, very much like Iris or MNIST. And at the end of the day, it predicts, are they next to each other? Or is it a sequence or not? So is not next or is next? So you know this because you're taking this from the text. So if you take the owl flew here, and then the next sentence was, then it flew away. When you're training, this is going to be 1, correct? And this is going to be a 0. you can provide that. In other examples, you would take one sentence from here and another sentence from over here. You put them together, and in the train set, this value would be what? This would, no, not next would be 1, is next would be 0. You see that? And this is how they also train the BERTs. So that's it. That's literally how BERTs work. So they're basically just GPTs or transformers, but they were trying to see if the sentences were next to each other or not. Okay? Any questions? So yeah, so that's basically it. And then finally, with the encoder decoder transformer, if you notice, the block has one additional thing. So multi-head attention, fully encoded layer, but it's got this in here. Okay, I'm not going to cover this one. This is for the translation problem, but this is just to illustrate that in the actual transformer, this one, this decoder layer, when you have an encoder and a decoder, needs to have a mechanism to deal with this encoder output. Okay, so instead of looking like this, it needs to have an additional layer in there. So this one has multi-head and fully connected, and this one needs to have multi-head, fully connected, but in between there's an encoder decoder attention layer. And its only purpose is to deal with the encoder output that comes into the model to somehow provide information about that for the translation. All right, I think that is it. So hopefully you're either relieved or you're happy, but either way, we are done. Right, so that's kind of the theory of transformers. So there's quite a bit there, but that's actually what I wanted to discuss. Any questions? No questions? Everything makes sense? All right, great. All right, so let's see. So the next thing I was going to do is just go back to the Hugging Face examples and just kind of work through those. So do some of those examples in the repo, basically. All right, so let's open up the GitHub. I'm going to open Anaconda. Okay, so we looked at GPT, right? And then I think we did some of the examples of BERT models. Okay, so let's go to the repo. Okay, transfer learning. Okay, so basically we started the class, did some examples of just using Hugging Face. We did a simple GPT. We did a few simple BERT models. I assign the homework, right, and the mini project, which is using this RLHF idea, okay? Then I went over the theory of transformers. We've discussed BERTs, GPTs, so I'm done with all the theory pretty much. So hopefully you guys understand the inner workings of these models. You have seen most likely that they're complicated, right? So you've seen that they are very complicated to implement, but I would say that it is important to have a sense of how they work. There's a lot of, there's basically PyTorch or TensorFlow, which is how you can program them at the low level API. And then there's a lot of abstraction, right? So there's a lot of abstraction, even in PyTorch. Hugging Face is basically a higher level of that abstraction, right? So it's basically to simplify things. And so Hugging Face has created a lot of examples that they have on their repo on how to use these models, right? A GPT or a BERT for specific tasks. So now for the rest of the time that we have, we can focus on just the different things that we have available in Hugging Face and think about maybe trying to solve some problems. So at the end of the day, if you think about what you're doing with your GPT, you're just training it to kind of sound like Shakespeare or kind of sound like Rick and Morty or kind of sound like Harry Potter or something like that. But that doesn't solve problems, right? Fine-tuning a pre-trained model is what starts to solve a problem, okay? So then there's a lot of things that you can use these models for. So this is the Hugging Face folder that I have. And as you can see, I have examples here of started with the intros and GPTs, but there are other things that you can do. So there's specific tasks that Hugging Face doesn't just have text. In fact, it's got ways of handling audio and video. So you can look those up. There's a lot of information there. I will just focus on text though, but that's available. And then there's fine tuning for various tasks. Okay, so like sentence classification, etc. So we have that. Yeah, there's, because these are embeddings, there's also ways of measuring the similarity of things. Okay, so what I was thinking is we can go to Hugging Face actually. And let's try to do an exercise here. So this is the best place to go to. These are all the tasks should be here. So transformers. Okay, oh, here they are. So this is what I was saying. So there's lots of things like dealing with multimodal data. There's dealing with computer vision, which is not something that I've done a lot of. There's the natural language processing task. So in this case, we've got things like question answering, zero-shot classification, which we have done, translation, sentence similarity, which is basically, if you can think of as taking a sentence, creating embeddings, and then comparing them. Fill in the mask, which is what we've talked about. We've got audio tasks here and various other things. So there's really a lot. So let's take a look at one of these examples. For instance, what would be a good one? High sentence similarity. Yeah, so you can see they've got all these models. All right, let's try the example I have here, actually, the text similarity. Let's do this. All right, so I'm going to go through this example, okay? Basically, we have sentences here. We're going to try to embed them, and we're just going to see how similar they are, okay? Based on the embeddings. All right, so this is sentence embedding and semantic text similarity, okay? So we're going to need a lot of libraries probably for this. So let's try it. Okay, so I'm going to I'm going to start the environment. Activate. The HF one. All right, thank you. So Pi 37. TS 530. Okay. Start the Jupyter notebook. All right, so this example will use a lot of, I saw in there, it has a library called Fair, I think, or Flare. And that's Flare, yeah, that's from Facebook, basically. Let's try it out. All right, so this uses Pandas, Torch, NumPy, and then it's got the Flare library for dealing with, and basically there's a lot of things of embedding. So if you notice, it's got word embeddings, document RNN embeddings, transformer document embeddings, sentence transformer document embedding, and so on. So a transformer is an embedding machine, right? You got a sentence and you get an n by 40 by 512. That's an embedding. There used to be a thing called word2vec many years ago in 2014, right? And the word, you would also have words and the words would have embeddings, okay? So at the end of the day, it's just vectors that represent the words. So the idea with this problem is you want to take two sentences, okay? And you want to compare them. So you want to say the horse is going really fast. The car has an engine. They're not very similar, right? Versus the horse is going really fast. The donkey is slower. Those are more similar. You see that? So this is the type of problem that we want to solve with this. So this example basically is going to show us if we use classical word embeddings from 2014 versus the embeddings that a transformer would create, which one does best. Okay, that's basically what we're doing. Do you guys see the idea? Now, hopefully the idea of embedding makes sense at this point, right? You give it a sentence, all the neural networks create a vector of n by 40 by 512. All right, so this is the task that we're going to try to solve. So let's go ahead and run it. So obviously a lot of libraries are going to be missing here. Let's go back here. I'm pretty sure Flare is not installed on this. Okay, so Flare, yeah, it's missing. So let's add Flare. So Flare. Did you guys run this? Did it install for you? Huh?
Still doing mine.
It's still doing? So what would you expect if we're comparing word-to-vec embeddings to RNN embeddings to transformer embeddings, and they're all basically the idea is to compare two sentences to determine how similar they are, what would be the outcome that you would expect? Which one would be best in theory? Maybe not in practice, but in theory. And why? Let's say that was an exam question, actually. What would you answer? And why? You guys understand the problem, right? We're going to take two sentences of any kind and compare them, but we can't compare the words, right? We're going to create embeddings, just very much like transformers create embeddings. So we're going to use word-to-vec, we're going to use RNN embeddings, word-to-vec embeddings, or transformer-based embeddings. So we would convert each sentence based on whatever the technique is, compare them, and then determine if they are similar or dissimilar. So what would you expect would be the outcome? Which of the methods would be better in theory and why? No idea. Why transformers? Exactly. Because of the attention mechanism, the embeddings are better. You see, exactly, that's the whole point. So the whole point of this is that transformers create embeddings. That's like the secret, right? At the end of the day, it's just embeddings. It's a game of embeddings. Before you had word-to-vec. Word-to-vec, you can literally download a list of 100,000 words with embeddings of size 128 for all of them. But what's the problem there? The word bank only appears there once with the embedding of 128. That's what we're going to use. That was 2014 word-to-vec. In today, we have a transformer, either a BERT or a GPT, it doesn't matter. We run the sentence, right? And it's going to give us embeddings all the same, but this embeddings, as you said, are different because when you give, the trick is you have to give it the whole sentence so that it looks at that cat is sleeping on the couch or the bank of the river versus the bank of money. So the output of the word bank varies based on context. And that's only accomplished with attention mechanisms. Now, other models, other neural networks can have attention. Like you could add attention to an RNN, I guess. But I'm just saying the transformer has that built in. So in theory, the embedding should be better. So as you said, in theory, then it's got a better understanding of the two sentences because of that. And therefore, it, in theory, should be better. Now, will it? I mean, that's a different thing. But in theory, that's the point of this exercise, okay? To kind of illustrate that point. Okay, so it installed Flare. That took a long time. All right, so let's run it. Did it run for you guys? Finish? Still running? Still running? What? You're not, okay. Oh, it finished, okay, great. Got the libraries. You know, this is always like, takes forever. Anyway, so this is the exercise. Probably one thing I will do is briefly cover Word2Vec, because the algorithm can be quite complex, but we'll talk a little bit about how that is calculated. But at the end of the day, as I said, it's all about creating embedding representations for words. If you get confused about this idea, just think of the classical approach in the past, right? To represent the word, we would create a vector. And this is not even that long ago, maybe 15 years ago. To represent words, we would create vectors that were the size of the vocabulary itself. And then what were the values in that? Basically just a 1 for the word and 0 for everything else. So effectively, we would have vectors that had all zeros and then like a 1. And that was called a very sparse vector representation. Do you see that? That was bad for machine learning. What people wanted was a very small vector of size, not 70,000, but with all zeros, but 128 with a lot of values in it. Do you see that? So that's the breakthrough with Word2Vec. And transformers just take that a step further by still creating vectors that are dense and small, but with the attention mechanism, which provides better results. Okay, so that's kind of the intuition here. All right, so hopefully that makes sense. So let's try this exercise, right? So the idea with this exercise should be that we need some sentences. So let's go to the GitHub repo. Okay, so we've added this. So let's grab this one. Some examples here, and you guys can help me out. All right, so I have sentences here that are similar. A black dog walking beside a pool. A black dog is walking along the side of a pool. Then I have a blonde woman looks for medical supplies for work in a suitcase. The blonde woman is searching for medical supplies in a suitcase. Number 3, a doubly decker or double decker red bus driving down the road. A red double decker bus driving down a street. There's a black dog jumping into a swimming pool. A black dog is leaping into a swimming pool. The man used a sword to slice a plastic bottle. A man sliced a plastic bottle with a sword. Do you guys get the idea, right? So these are very similar pairs of sentences. We need to take these as text and code them into embeddings and then compare them with some metric to measure similarity. And we're going to use several techniques for this, okay? So let's go ahead and run this one. All right, we can print these out in a PDF frame. Okay, you have them there. Sentence 1, sentence 2, okay? Now, there's also going to be dissimilar sentences, and as you might expect, the similarity scores for these are going to be lower, okay? So we can take a look at that. So here, the dissimilar sentences, a little girl and boy are reading books. An older child is playing with a doll while gazing out the window. That's what it means to be dissimilar. 2 horses standing in a field with trees in the background, a black and white bird on a body of water with grass, I guess, in the background. Yeah, in the background, right? So those 2 are dissimilar. So these are the pairs. 2 people are walking by the ocean, 2 men in fleeces and hats looking at the camera. Then a cat is pouncing on a trampoline, a man is slicing a tomato. Different. A woman is riding on a horse, a man is turning over tables in anger, right? So these are the dissimilar sentences. Okay, let's print. Okay, now let's go ahead. All right, so we're going to have a function. Okay, takes in S1 and S2, right? They're going to be already of whatever type we're using, whatever mechanism and flare we're using for the embedding, S1 and S2. And then it's just going to take a cosine similarity between S1 and S2, and that's going to be the score. Okay, cosine similarity is just a math operation in algebra that is used for measuring the similarity between two vectors in a vector space. Okay, guys? So you could also, another way of thinking about it is, think of this space as three-dimensional, right? And so you have people represented as age, height, and age, height, and weight. So let's just concentrate on age, right? So all the people that are older, they're on an axis, this axis, right? So that goes from 0 to about 100, correct? So people that are 80 are going to be high in this space. Do you see that? And babies are going to be down here, right? And so that's basically what's going to happen. You're creating embeddings of these sentences, right, that are going to be represented in a vector space. So then you can take a measurement of it, right? So you can take a distance between the two vectors, and if they were close, right, then that means they're similar. If they're further apart, they're dissimilar. Do you guys see that? So you all understand that intuitively. The cosine similarity is just like a very special representation of that. I didn't bring the equation, but it's just, trust me, it's what everyone uses, and it's the better approach than just a straight distance between two vectors. Does that make sense? So we're using that, right? So then all we need in this example is, if we have the cosine similarity between S1 and S2, which gives us the metric, all we need is to represent our sentences as these embeddings, okay? And that's what we're going to be using from flares. I'm going to go ahead and load the sentence, the function here. Okay. Okay, so this function then basically is going to take, you can see here, the list of sentences, right? We are going to need the embedding object. It evaluates the embeddings here, calculates the similarity score, which is this function over here. And it's going to, let me see, there's a class here. Iterate. I'm trying to find this function sentence. Oh, here it is. Sorry. Yeah, I knew it was. It's right there from flares. Right. So we're going to use the flare sentence. We give it the input, and it's going to process it. There it is. Okay. So we give the two sentences, create S1 and S2, and then S1 and S2 get embedded based on the embedding technique, such as running it through a word2vec, running it through a glove, running it through a transformer. At the end of the day, what matters is we get a sentence and it converts it into an embedding. All right, so let's go ahead and add that in. Add a few more cells in here. Okay, so we can go back. So there's several techniques. There's this one called average word embeddings with glove. There is this one considers sequence using an RNN with GRU. So these are involved procedures, okay? This is not just like one simple thing. These are very involved. You know, an RNN is a specific type of deep learning algorithm. So it's a technique. And then we have BERT, you know, sentence BERT basically, right? So this is a specialized BERT that creates embeddings kind of discussed this previously, right? You give it a sentence, it produces an n by 40 by 512. So that's what you can try. Okay. So let's do that. Okay. So I'm gonna try the first one, which is glove. Glove is like Word2Vec. It's just a more advanced version, but it doesn't have attention, right? So this would be like the 2014 version. Okay. So let's go ahead and do that. Okay, so how does this work? So we go to the word embeddings object over here, right? Word embeddings from Flare. And we specify that we want to use this technique glove. So this gives us embeddings for words as was the state of the art in 2014. No attention, but they were definitely better than, you know, a vector of just the vocabulary. Okay, so we have glove here, and then, you know, we take the embedding and produce glove pool embeddings. Okay, so let's try that. So now let's evaluate it on both data sets. Okay, so this is the glove average embedding. So it takes in all the sentences that are similar and dissimilar, which are the data sets here. So this is dissimilar and this is similar. Okay, there are 1, 2, 3, 4, 5 pairs, correct, of similar, and there are 1, 2, 3, 4, 5 pairs of dissimilar. Okay, so before I run this, what would you expect for the values? So in theory, these similar ones should be more similar, right? Closer to 1, and these dissimilar should be further from 1, right? So let's see what happens. So what do you guys think? There's like an overall average, and then there's for each one. So what's your interpretation of this? I mean, this is what it is. I mean, it's not. What do you guys? So the similar are more similar than the dissimilar, right? Because they have a, now the difference is not really that big. It's 94 and 98. Do you see that? This is, make sense? Questions? Yeah, I agree with you, but so let's try another method, all right? So let's try another method. Okay, so I'm gonna use, so we got these values. You can see it's exactly what I had. Consider sequence. So the first one, glove, is an averaging. So I wrote here average word embeddings with glove. What does that mean? It means that it takes a sentence, it embeds each word, and then what does it do with them? It just averages all those embeddings to create one final embedding that's the average of all. Why can you do that? Because the embedding size is the same for all representations. Does that make sense? So then you can create an average. In this next technique, RNN GRU, it says it considers sequence. So that means the cat ate, right? So 8 came after cat, right? So that's what that means. So let's try that one. Excuse me. Okay, so that's the GRU embeddings. I'm going to repeat the exercise, but with another technique. Same thing, GRU RNNs. I evaluate similar and dissimilar, correct? Just like before. Hit run. What do you see now? What does your intuition tell you? So now the average is 97 to 91, right? This one, for instance, 1 to 89 is good, 92 to 85, 99 to 88. Do you see that? So it's better in theory. This is why what you were saying. Why aren't they more? Why is the gap not bigger, right? So the gap here was 98 to 94. The gap here is 97 to 91. What do you attribute that to in this one? So the original embedding was just an average. This embedding considers what? Sequence, right? That's what it says. RNN grew. So when the embeddings are calculated, the cat is sleeping on the table. So the order matters. Okay? Let's try another one. So we did this one. Now the following execution instantiates a BERT base on K. So this is from Hugging Face model that pulls the final layer as a non-specific BERT base. So here you just create the embeddings. It's not a specialized, right? What that means is it hasn't been fine-tuned for any task, right? It's just an embedding. Okay. Notice it's not going to be better than glove. So I'm going to do control copy. Right, it's taking a bit longer. Oh, it finished. All right. So we're going to try this one. We're not training the model. Where's the other one? Oh, there it is. We're not training the model here, right? We're just doing inference on this BERT model. Okay, so let's read again what's written here. So it says the following execution instantiates a BERT-based on-case model that pulls the final layer as a non-specific BERT. That means literally it's just the BERT that you basically run data through it, right? Like in one of the mask problems or something like that. Does that make sense? So it was trained just for that. So it's a pre-trained BERT. It's actually not better, okay? So what does that mean then? It means that you should take that BERT and fine-tune it for this specific task. Similar and dissimilar, okay? So the first BERT that we're using is a pre-trained BERT with no fine-tuning. This next BERT, so that's what this is saying. So BERT not specialized embeddings, it's not better than glove, actually a bit worse, okay? Because it's not a good idea sometimes, or in general, to use like GPT just pre-train or a BERT pre-train. It's not enough. They know stuff, but they're not great at the task. Now, from the Flares library at Facebook, we use something called sentence BERT, which is now a specialized BERT for this task. All right, it has been fine-tuned for similar and dissimilar, okay? So I'm going to try this one. Okay, so we need to load this one. Oh, no. The library sentence transformers is not installed. It says. To use sentence, please first install pip install sentence transform. Okay. Did you guys get this error? You guys didn't get it. It worked for you? Oh, why didn't I use it? Okay. All right. So it, okay. And then, did you uncomment this? Yep. Okay.
No, I didn't.
Sorry?
It
It works without it. Okay. That I see. That's why I had it. So you don't need it. Got it. Got it.
Just we can install sending transformers.
Yeah, and it worked. Yeah. All right. Great. Awesome. All right. So then I'm going to go down here. Hopefully this time it'll work. Oh, I finished. All right. So now go over here, run these. What do you think? You were protesting, right? What did you guys learn from this exercise? This is very fundamental, actually, as it turns out. It's all about these embeddings and the quality of it. You see that? So let me go to the whiteboard for this and kind of summarize it a little bit. So it's a little bit important, I think. Stop sharing. And I'm going to go to the whiteboard. All right. So a little bit of history here, right? So when I started in NLP, this is what we did. So I had, you know, cat, dog, car. We still used embeddings, but we used something called the bag of words approach. I did this for many years. Bag of words approach. What was this basically? You created vectors, but they were huge. If the vocabulary was 70,000, then literally this was 70,000. What does that mean effectively? If you're doing a sentence, the word cat is going to appear once. So each entry here was the actual word. This is what you did. So for this one, this is a 1, this is a 0, this is a 0. All think about how many zeros there are in there, and then just a 1. Oh, this is dumb, sorry. Dog was a 1, 0, and a 0. Car, 0, 0, 1, but just 70,000. You'd literally look at this matrix and you would swear there's only zeros in there. Okay, and this was called, maybe you've heard this term before, a sparse matrix. Maybe you've heard that before. That's what this was. This was the problem that everyone hated, right? They didn't want to do this thing. So in 2014 came Word2Vec. Maybe you've heard of Word2Vec, right? So Word2Vec is a famous paper by Mikolov, probably from Google, I think. And they just said, what we want is, we still want cat, dog, car, but we don't want any more of that gigantic vectors with all zeros in them. Instead, we're going to create vectors and we want them to be small. Do you see that? They need to be small. And they started, I think the original paper was 128. They set this at 128, the size of the vector. What are those in the previous one? Every word is a column, right? You knew that intuitively as humans. Here they said, I don't know what these are. They're just F1, F2, all the way to F128. But we don't know what they are. We just fix the vector. The other condition is that it needs to be dense, no more sparse. Everything needs to have a value, okay? So Mikolov and his team created Word2Vec, which was basically something like this. I have a diagram in the book online, but it's basically like this. You would take words and you would create a neural network, okay? So you had some word here, and the word would go through the neural network and then was mapped to some task over here, this was words. So this would be like words from 1 to 70,000. And over here, you have the same thing, 70,000, okay? But each word could be represented here, was embedded to 128. Do you see that? You would set this layer to be 128. Do you guys understand? Remember that if you have 128 neurons here, and it's a fully connected layer, what does that mean? That this word is connected to all 128 neurons in that neural network. Do you see that? So effectively, you would use those weights as the representation of the words once you finish the training. Do you guys see that? That's basically what you would do. I give it another word here, right? There's 128 neurons, correct? Fully connected, what does that mean? I have 128 weights here. Do you see that? And the same thing applies over here. I have yet another word, 128 neurons. So I have 128 connections. I would use those weights to represent that word. And that's the trick that they invented. So now you would basically train the neural network. So at the end, what you have is, given a word, you're going to get the set of weights that belong to it. And that's it. That's the representation. That was Word2Vec. And so we got away from this zeros and ones thing to now we had these vectors that have size 128 with values, which were the neural network weights. Does that make sense, guys? Any questions about that idea? What was the problem with that, though? The problem with that is the word bank, for instance, only appeared in here once, right? And so whether it was Bank of the River or Bank of Finance Money, yes, they both had the same set of weights. The transformer is an extension of this. Transformers do, hopefully by now, you're bored of me hearing that you have an encoder, something like BERT. We're using a BERT here. You give it a sentence. The sentence goes through all the embeddings, right? And what you get out here is n by 40 by 512. So you still, for every word, so these 1 to 40 are embeddings, just like before. But what's different about this is you don't, in Word2Vec, you can literally store this in a file. Like I literally can go and get a Word2Vec or a glove file, and I'm going to look up bank, and I have its embedding of 120. Got it. Transformers don't work like that. You can't store embeddings of words. Why? Because in the transformer, you have context. So the only trick is you have to give it the whole sentence. So in a transformer, you give it the full sentence. People were walking on the bank of the river and they slipped, right? It's going to run that entire sentence through a BERT on case or whatever it is, give you a final embedding at the end, and you just have to know, okay, I'm looking for the word bank that was embedding, that was ID 17. So over here, I just look for ID 17, and I've got now its embedding of, so it's going to be word 17, right? It's an embedding of size, oops, sorry. It's an embedding of size 512. But it runs through the transformer. So the embedding for the word bank that comes out of the transformer depends on the other words in the input sentence. If I had entered yet another sentence related to something else about banks, Joe Banks, I don't know, versus the volcano, right? That's not clear if it's one or the other. So that sentence goes in. Will it have an embedding like Bank of the River, an embedding like the financial institution, or yet another embedding? It'll have another embedding, right? Because it depends on the context. So all the attention mechanism, remember, that's happening here is paying attention to all the words, and all of that is activating to produce the final embedding for the words that come out over here. That's a really important thing. That's why I said several times, something like a BERT is basically an embedding machine. Do you guys see that? That's the power. So the attention just produces these really good embeddings. Now, the other thing that we saw in the problem that we were doing is that when I tried to use a BERT just pre-trained, it wasn't actually very good, right? So they do produce embeddings. They are paying attention, but it's probable that it's because you're giving it so much data or whatever it is that it isn't quite there yet. It's like the information is there, but transformers work better when you fine-tune them. So you pre-train them with a lot of data, and it's there, and then you do the fine-tuning part. I can't answer why. I mean, I don't know that people know exactly, right? Not everything about transformers is known, but in practice, as you can see right here, right, something like a fine-tune, what is this one called? BERT-based NLI mean tokens, right? A fine-tune BERT, so it was pre-trained and then fine-tuned, did what I would consider a really good job on sentence similarity. I don't know if you guys agree. So 48 to 98, 41 to 95, 19 to 96, 0 to 100. 0 to 100, right? So it did a pretty good job of answering, are they similar or dissimilar? Does this make sense, guys? Are there any questions? So this is an important concept because it shows that, the fact that these embeddings are really important. That, I went over the history of it, kinda, and then I showed the RNN had sequence, and the BERT base basically is a fine-tuned model. Okay, yeah, any questions? That's basically the idea. So the good part is no more theory, right? So that's week 4 is now, right? So we are currently on week 4. The exam is 2 weeks from today on week 6. It'll be a written exam, closed notes, but you're allowed your cheat sheet on 8.5 by 11, and you can expect most of the questions will be of, how does BERT work or GPTs, and there will be some coding, but I'm just looking for logic. Okay, so really just your understanding of some of the basic ideas, what is attention, etc. Okay, so that will be, and also, did we say that the homework is next week, right? So the last half of next week, a week from today, you guys will do basically your demos of your pre-trained GPT. Got it? And then so next week, I'll probably just do more code examples like this one. And I'll bring in that linear algebra example, and then you have your mini project, right? So now I've given you the GPU, so you can start playing with that. Let me know if you have any questions on the project. Okay. But, I think this concludes some of the important ideas of transformers. So let me stop. I'll stop the recording at this time. And then if you guys have